All right. So I'll be waiting for some of them to join. Okay. Okay. If anybody has joined, please can you just shout me up there? Yeah, I think I can see one. All right. Gladys, I think, okay, remain 2 minutes. Um, Immediately is 8 o'clock. I think I will just start. So let's just wait for 2 minutes. After that, I start. All right. Just 1 minute. Then we'll start. All right. So let's start our class. Okay. Gladys, can you help me also share the link to others so that they can join on time? Thank you. And then Gladys, I hope you can hear me properly, right? If so, just give me a thumb up. Okay. Now, let's start. I think I'm having people in the room now. Okay. Okay, so we are going to look at the elementary mathematics, which is the set theory in the elementary mathematics. Okay. So my name is Babarin Saolaiwala. I'm here to make mathematics understandable as possible. All right. Now, so we are going to look at the set theory. Let's talk about the introduction to set theory. First, let's do the definition of set theory. Set theory is a fundamental branch of mathematical logic that studies the nature and the relation of collection of objects known as sets. Set provides a foundational framework through which virtually all mathematical concepts can be described and understood, enabling mathematicians to rigorously define objects and ascertain their relationships and then the properties. Now, we look at the importance of uh, set theory in mathematics. Okay, importance of set theories in mathematics. Set theory provides the basis for various branches of mathematics, including analysis, topology, and algebra. It plays a critical role in defining functions, limits, and cardinality, fostering a deeper comprehension of mathematical structures and their interrelations. All right, seems also we talk about the history and the contributors to set theory. The formal development of set theory began in the late 19th century, spearheaded by mathematicians who sought to establish a more rigorous foundation for mathematics, leading to significant advancements in logic and philosophy. It seems I can't see some of you again. Okay, let me just wait 2 minutes for others to join. It seems they're joining late. All right. I think I will just continue instead of waiting for others to join. They'll definitely see the video later. All right. Now we talk about the history and the contributors to set theories. There are some mathematicians that spearheaded uh, the contribution to set theories. So we're going to look at some of them. Now, we have George Cantor, is regarded as the founder of set theory, who introduced concepts such as infinite sets and cardinality, establishing a hierarchical of sizes for infinite collections. His groundbreaking work laid the groundwork for understanding both finite and infinite sets in a rigorous context. Now, we also have Bertrand Russell, contributed significantly to set theory through his work on the foundation of mathematics, particularly highlighting paradoxes. His foundation of the Russell paradox raised vital questions about self-referencing sets. And the last person also is David Hilbert. His contribution to set theory include his foundation work that sought to provide a complete and consistent framework for all mathematics. Now, these are the contributors. We have many, but these are the renowned contributors that contributed to the set theory. And then George Cantor is actually referred as like the father of set theory. Okay, which link? Yeah, the recent one is the one you just joined. Okay, maybe that is the problem there. Okay, because I'm having some other people here joining. Okay, now let me just continue. Now, let's talk about the application of set theory. We have not done the set itself. We are just talking about the set theory first. Later, we're going to talk about the set. The application of set theory. We have the real-world applications. Set theory serves as a foundational principle that underlies various domains from statistics to data-based theory, encapsulating everyday phenomena such as classification and organization of data, enabling clearer communication and problem solving. Now, we also use it in computer science. So in computer science, set theory enhances algorithm development, database management, and then design of programming languages. It informs data structure development, enabling efficient operations like searching, sorting, and database querying. Now, we have many applications, but these are just for the real world and for the one of the computer science. Now, so let's talk about the set itself. That is the set theory. Now we're going to talk about the set. For the set, in mathematical terms, a set is defined as a well-defined collection of distinct objects known as elements or members, which can be anything from numbers to letters to even other sets. The ability to determine whether an object is part of a set is fundamental in set. Now, let me explain this one before I move further, where I will also try to write. Now, set is just the collection of distinct objects. Any object. You call about the family, it's object. Talk about the letters, yes, object too. Numbers, even the letters we have different. We have the vowel letter, the consonant letters, okay. And for the numbers, we have the, okay, okay. For the numbers, we can have the even number, the odd numbers. All these give you the distinct object. We can also refer to cars, different brand of cars, Toyota, Tesla, and so on. Or you want to refer to the company. That is why it's collection of objects, distinct objects. Any, but it has to be a distinct object. Now, sets are commonly represented using curly brackets or curly braces and denoted by capital letters. For example, a set of natural numbers can be denoted as 1, 2, 3, and so on. The notation X equals X property of X. Now, what this means is that it expresses the set X, the capital one, in terms of its elements properties. Now, let me write and explain this one. Oh, sorry. Okay, in this place, now here, this is what I want to explain, please. I want to write something here. So we use capital letter. Okay, it can be capital X or any other. Oh, seems nobody's saying that. Sorry, it seems nobody's saying that. I hope you are all with me. We share the screen, please. Okay. Now, okay, let me share my screen now. All right. Okay, sorry for that. Now, as I was explaining, let me go back to that. So I said we use curly braces for set and then capital letter to represent the set itself. So like if you use capital letter B or A, that is a set. And its elements would now be in small letter. Now, if you have the A, you can have some elements in A like A1, A2, A3, and so on like that. So you can see that the elements are we use small letter A for the element, then the capital letter for the set itself. All right. And there must be a curly bracket there. If you definitely use ordinary bracket like this, that is not a set. If you use a square bracket like this one, that is not a set. It must be a curly bracket. Something like this. Then the other one. All right. So this is how you know that okay, this is set. Okay, let me erase that. Now, let's look at some examples of a set. Set of the first five natural elements, sorry, natural numbers, 1, 2, 3, 4, 5. This is the set of the first five natural numbers. You know, we did natural numbers last time. They are just counting numbers. And when you are talking about counting numbers are just numbers, you start 1. Okay. Like when I asked that time, someone should tell me the naturally tell me the count numbers for me, and she started from 1. So the same here. So 1, 2, 3, 4, and 5. Okay. Another one is the set of vowels in the English alphabet, the A, E, I, O, U. Okay. Then we also have a set of days in a week, like Monday, Tuesday, Wednesday, Thursday, Friday, Saturdays, and Sunday. We have set of even numbers. The set of even numbers. Now, here we are being told there's a bracket there. We are being told that between 1 and 12. So that means we only look at the natural number, sorry, the even numbers between 1 and 12 only, which are 2, 4, 6, 8. Actually, there's a 10 there. Okay. There's a 10 there before 12. Sorry for that. 10, 12. Okay. Next is set of prime numbers less than 10. So if you can still remember prime numbers that are less than 10 should be 2, 3, 5, and 7. These are prime numbers that are less than 10. All right. Thank you for joining. Okay. Okay. I can see. But there's something you need to know when it comes to sets. Remember this, the examples I gave here, we have numerous examples, but these are just the few examples of sets. Remember that sets are distinct collection of distinct objects. Okay. Now, there's something you need to know about set. The first is that order of element in a set does not matter. For example, you said father, sorry, son, daughter, father, mother. It doesn't matter. It's a family. Family is a set. The elements there are the father, mother, and the children, or let's say the son and the daughter. However, it's not necessary that you have to start from father, mother, son, daughter. You can do it anyhow you like. That is the order of the element in a set does not matter at all. Okay, I hope you understand this. Now, the next one is that the elements in a set are unique and cannot be repeated. So you can't have father, father. Definitely you can't have two fathers. The only one can't have two fathers. It's only one. All right. Then if you have, like, let's go back to this example here for this set of prime numbers now. For this set of prime numbers less than 10, we can't say 2 2. We can't write 2 twice. 2 and another 2 again. We can't write it twice. It's not possible. So it's only once you are going to write it. Okay. So you cannot repeat that. Okay. Next is that sets are usually represented using curly braces. So here we are going to use curly braces for sets. Okay, you can't use any other thing. So at least you have to know these three things so that when you are giving an example by yourself, you should know what to do. So you don't repeat the element in a set, and in the order how you arrange that set does not matter. Like the example I gave you. Now, for that example of this last example, set of prime numbers less than 10, I can start from 7, 5, 3, and 2. I've written all the elements, but they are not in the way we used to look at ascending order. It can be anyhow. I can even write 7, 2, 3, 5. It doesn't matter. So the order of the elements does not matter. However, the elements we have there have to be unique. It has to be unique. And you don't repeat them. And then you use the curly bracket. These are the things you need to know in sets. All right. Now, let's talk about the representation of sets. We have a tabular or roster form. This is a form of set representation where all the set elements are listed separated by comma, and they're enclosed in a curly bracket. Now, let's look at an example. For this example, we have A equals 1, 2, 3, 4. Now, can you see that we list all the elements and we put comma there? 1, after the 1, there's a comma there. 2, comma, 3, comma, and the last element 4. Okay, and we put it inside the curly braces, right, or the curly brackets. Now, that is a tabular or a roster form. Let's look at another example of that. B equals 0, 2, 4, 6. This is set of even numbers from 0 to 8, or less than or equals to 8. So we wrote all the elements out, okay, and then we put comma there. Now, this one is the is for vowel letter A, E, I, O, U. So for this A, E, I, O, U now, we have there are 5 in numbers, and then we put them inside the curly bracket. Another one is D. So let's say group of friends. For this group of friends, we have Tom, Dick, and Harry. Okay, we have the Tom, Dick, and Harry. I think someone is saying the link is not working, but definitely let me resend another link. But I know that's how others were able to join. But let me let me copy this link and give them. Okay. Most people are complaining the link is not opening, but definitely is opening. All right. Now, so let's continue. Statement form. There's another one. This is by defining a set of as a sentence. Sorry, you define this set as a sentence. For example, we have B equals odd numbers less than 9. You see that it's just like a sentence or a statement. That is, we are not given what is the elements there. So you'll be given in a sentence or in a statement, then you turn it to list. Okay, you turn it to list. Okay. All right. Then the next one is K equals all letters of alphabet. Oh, sorry, that should be P. All letters of alphabet. Then we have another one called the set builder form or the predicate form. This is a form of set representation where a rule is defined for an element to satisfy for it to be a member of the set. So there's a rule that is being defined for that one. So you have to follow the rule. If you don't follow the rule, you will not get the elements that are there. So you have to follow the rules. Now, for example, you have C equals this. Now, in this case, now you can see that it's neither a statement or in a tabular form. So you have to do some kind of calculations a little bit to know your element out. Or like the statement form, the odd numbers less than 9. You know all the odd numbers less than 9. 1, 3, 5, 7. Okay, since they say less than 9, you can't pick 9, right? Now, but for the set builders, it's totally different. Now, we said x is a member of the natural number 5 less than or equals to x, 5 less than x less than 10. So you have to look for the numbers that are in between. But remember that is 5 is less than x, it means that x is greater than. I believe you still remember how to do those things. If you have 5 less than x and then less than 10, okay? For example, normally, remember in normal, when you are doing calculation, x used to be on the left side, right? When you are calculating the value for x, it's usually on the left side. So let's first divide this thing into 2. We have 5 less than x, and then we have x less than 10. You know, I said and we have, so let me use this sign symbol for and there. Now, here is already okay. Why? Because the x is on the left side. But for this, it's not, because the x is on the right side. Now, 5 less than x. If you want to make x on the left side now, what you have to do is just take a mirror, place it in front of this what you have written. Then you will see that it's going to give you what we call a mirror image. So it's going to be x greater than 5. That's what it's going to give you. Now, okay, so that means x is greater than 5, and then x is less than 10. Okay, now what are the numbers that are greater than 5? Remember, they say s is greater than 5. It's not x is equals to 5. Greater than 5, we have 6, we have 7, we have 8, and so on like that, right? Let me just put dot. Now, this and is the dot that we have here. Now, let's talk about x less than 10. What are the numbers that are less than 10? 9, 8, 7, and so on. Backward, right? Now, can you see that it means that it's starting from 6 and it's going to end at 9. So at the end of the day, we have 6, 7, 8, and 9. These are the numbers we have. Now, you can see that I've written it in the tabular form now. So that becomes my C equals this. Okay. So that's what I have. Now, another question, we have x squared plus 2x plus 1 equals 10. So in this case, what happened in the set builder is that you have to do a little bit calculations. You have to find the values for your x. So when you do it, it will now form a tabular form. It's not being a set builder anymore. Okay. So you have to do the calculation of x here to know the value for x. You know, this is now quadratic. Oh, we have not done quadratic. Definitely, we are going to talk about quadratic, I think, next class. So let's talk about the fundamental terms and concepts in sets. The first is what we call cardinality. Cardinality refers to the numbers of elements within a set, a crucial concept allowing mathematicians to compare the size of different sets. Now here you can just use it to compare different sets, but let's look at some things then. It is denoted by NA, or the A with 2 vertical lines. Example, if you have A to be 1, A, B, 4, 6. Now, you might be saying, oh, why do we even have A, B, and then numbers together? It is the way we want to define it, and it is distinct. We say 1, A, B, 4, 6. No problem. How many? The cardinality now will be how many of that element, how many elements is in that set. So you have to look at how many elements we have in that set. Now, for us to look at that is very simple. You just count the numbers of the elements in that set. Okay, you count the numbers of elements in that set. Let's count the number of elements in that set. That should be 1. Okay, let me use it. 1, 2, 3, 4, and 5. So this is the cardinality of it. So we have NA equals 5, the numbers of elements in that set. Now, let's move on. Finite and infinite sets. Finite set contains a limited numbers of elements, while infinite set can extend indefinitely, such as the set of all integers. Now, finite means it is being contained. It is not more than what is there. For example, now let me just give you something. You have water, right? That water you have, if you put it in a glass, a cup, in a cup, the cup is now the container, right? And that cup that is the container has already enclosed it, meaning that it cannot go beyond that. So that is a finite. Okay. Now, but when we say infinite, look at the ocean now. It's infinite. You can't contain it. It's too large. Okay. Also, numbers, set of integers. Remember, we did integers. Integers are numbers either negative or positive with 0 also. So let's even talk about the positive aspect of it. For example, from 0 to, what is the last number we have? Nobody knows. So in that case, it's to infinity. So that's why I can say infinite sets. All right. Now, for example of this, we have D equals 1, 2, 4. This is a finite because it ends. The number doesn't go beyond the 5 and it doesn't go below the 1. Let's look at the second example. E equals 1, 2, 3 to 20. So in this case now, it means that it means that I'm starting from 1 and I'm heading at 20, even though there's a dot in between. I'm starting from 1, I'm going to end at 20. So I shouldn't write my number beyond 20 and I shouldn't write my number below 20. That is a finite one. Let's talk about the infinite one. The infinite set, n equals this. Okay, you can see now the natural numbers. Even we're even talking about the even numbers of the natural numbers. Sorry, of the integer. N equals 0, 2, 4, 6, 8, 10. We don't even know where it's going to stop. Sorry, the n is just the set itself. So 0, 2, that is actually like a whole number, but it's even aspect, the even part. Now 0, 2, 4, 6, 8, 10. We don't know where it ends. So that becomes an infinite. And if you want to know an infinite set, there's something that is a catch. There's dot, dot, dot. That dot, 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 after the dot, 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 the next thing we have is the curly bracket, the close curly bracket. That's how to know the infinite set. Okay? Now, let me write something for you here. Like the example we did, 1, 2, 3, dot, 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 and I write 10. This is a finite one. It's a finite because it ends at 10. However, like this question we just try to look at, you can see that after that dot, 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 no number again. The next thing we have is a curly bracket. And that shows that that is an infinite set because it doesn't have an end. But immediately you write number there, it has an end. Or you write a letter there, it has an end. Okay. Okay. Now, let's talk about the equality set. Sorry. Equality of sets. Two sets are deemed equal if they contain precisely the same elements, regardless of the order of the numbers of times elements occur. That is, every element in the set A belongs to the set B, and every element in the set B also belongs to the set A. So we write equality of set as A equals B. So we can see it here, A equals B. Now, for example, we have 1, 2, 3, 4, and the B, that is for A, and the B is 3, 1, 4, 2. 3, 1, 4, 2. Now, in this case now, we can see, can you see it? We can see that, okay, the sets are equal, even though the way we write the elements is not the same. One is we write it in form of ascending order, 1, 2, 3, 4. That is for A. For B, we didn't follow any pattern. It's not ascending, it's not descending. Because after 3, we wrote 1, then 4, then 2. Well, what we have to look at is that the elements in A are they also in B? One is in A, which is also in B. Two is in A, which is also in B. Three is in A, which is also in B. Four is in A, which is also in B. Okay, that is it. Now that means A equals B. Now, if you want to ask question, you can also do the chatting. Then I will try to answer it. All right. So we have that. Now, the next one, let's talk about the subset. The subset of B. A subset is a set where every element is also contained in another set. Now, I will explain the difference between the equality of set and the subset. They are totally different. Now, we said a subset is a set where every element in is also contained in another element, in another set, sorry, facilitating comparison and classification of relationships among those sets. Now, if A is a subset of B, we denote it as A. We usually write it as A. Let me write it here. Then C, like C, then this, then B. Now, I will just always give you something like a catch. Subset. If you want to write S for S, right? You first write like C before you turn it, right? So when you are turning it, don't turn it like S. Turn it like this. Can you see the way it looks like? All right. That's how to know the subset. Like, like what I do tell is that I use a conventional method also sometimes to explain so that you usually understand this properly. So you want to write S for subsets, the S, you have to write like C first. Then the remaining part that has to go like S, don't let it curve like C in the opposite direction, but let it just follow that C. So let me rewrite S. You want to subset, normally if you have to write S, it will be like this. Okay, but we don't want to write like that. So we just write it like that. So it will like C and this. So then you see subset of C. Now there's something I'm going to explain. Now, if there is the possibility that A is not equals to B, then we say that that is a proper subset of B, and we write it as, you can see the difference. So for the proper subset, you see the way is ordinary like C. Okay, that's how you denote it. Now, what do you mean by subset and the uh, different, this equality of set and the subset? Equality is that every element in that is also in that one, right? But when it says sub, anything sub is under. Okay. Now, let me give example. For example, let me use Agbola family, for example. So I just have to pick something. In Agbola family, let's say A. Okay. Oh, let me even use okay. Let me use Tinubu. Tinubu, let's use our president. T. Okay. For Tinubu, let me erase it and write it properly. You just want to understand this. Now, let's say Tinubu T. Now, Tinubu has children, right? Let's say Sheyi S. I don't know. Let's say Yaloja I. And then what else again? Let's say, let me pick someone's name here that I can use. Okay. Let's say Veracious V. Okay. Now, okay. But definitely, these are the children. The children are having children. That means Tinubu is now a grandpa, right? Okay. Now, if you pick S Sheyi, for example, now have let's say it has 4 children. Let's say Tokwe, Michael, let's say Farouk, and then let's say another one, Chibuzo. Okay, now we have this. Okay, now you can see that this S is inside, because if I have to expand this T properly now, I can write everything I have here and I replace it with this. For this X, I will not write this X again. I can now replace all this one inside it. So that means a set that is totally contained in another one. It doesn't mean that the other set is small or having the same thing, having the same element, the the biggest, there's a bigger set, then a fraction out of it is the subset. I think you understand what I'm saying. For example, now, let's see. Okay, let me give you an example. Shawarma. At least you will know that one very well. You have a shawarma. In that shawarma, there's sausage, every other thing there, and then you take part of it out. Okay, that part you take out is the subset. It's not the it's from the entire shawarma. You just take part of it out. That is a subset. Okay, you can put it back inside it. Okay, that what cause the subset. It's totally different from the equality of set. If it is equality of set, it means that what you are taking out and what is left, they must be the same. But if you take out of that shawarma, I don't think it will be the same. It will never be the same. So that one is totally different. I believe you understand. Then we have another one called the universal set. So the universal set is defined as the set that encompasses all possible elements relevant to a particular discussion or problem. It acts as a reference point within the contents of set operations and relationships. It is donated by you. We use you for universal set. Okay, we use you for universal set. Now, another one is the non-set. So for the non-set or empty set, the non-set denoted as this, that means nothing is inside it. Represent as a set that contains no element. If you don't have any element, sometimes you can also write it as this sign, like a fire, or this, anyone. However, please never write an empty set like this. You put a curly bracket, you now put this fire inside, and then you do it like this. This is not an empty set. It's not an empty at all. It's either you write this only or you put only the bracket without anything inside it. So for example now, for example, let A equals x, and the x is odd numbers and divisible by 2. Definitely there is no odd number that is divisible by 2. No. So since there is no odd number divisible by 2, then we say it's an empty set. So A is an empty set. Note that the empty set is not the same as I had, like what I just told you earlier. Okay. I can remember someone said, empty, null set. Say nonsense. I said, no, it's not nonsense, it's null set. All right. Then we have what called singleton. A singleton set is a special type of set that contains exactly one element, just one element, therefore serving as the basis for a larger set construction. For example, A equals 2. Now, A equals 2, you can see that 2 is the only element we have there. So that becomes a singleton set. That becomes a singleton set. All right. Now, power set. The power set of a given set A is the set of all subsets of A, including the empty set and the set A itself. It is denoted by PA, or 2 raised to power A. That is power. Anything power, remember, power, index, they are the same. Okay. For example now, let A be ABC, then the power set of A is this. Now, okay, how do we get all this one? Let me explain. It means that we are going to do some kind of permutation in it. Okay. Now, for this set, the first thing is that we can remove all the elements. If you remove all the elements, it will be empty. Nothing is there. That's why we have empty first. Okay. That is the first thing. Second, I can remove the remaining elements and leave A. That's why we have A. Next, I can remove every other element and leave only B. That means I will remove A and C. I will be left with B. Next, I can remove A and B and left with C. So I will have my C here. Let me erase that. Then next, I can pair it. So I can say, okay, let me pick only A and B and leave C. That's how we have AB. I can say, okay, I want to pick A and C only and leave B. Then next I can say I want to pick B and C and leave A. Okay. Then the next one I can say, okay, let me pick everything. That. Now, if you count all these elements we have within this set, you will see that it's 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 in numbers. Or you just use this formula straight. 2 raised power A. 2 to the power of A. And the A is the element in this set. Remember, like Na is the cardinality. So the cardinality of this is 3, right? The numbers of elements we have there is 3. So that becomes 2 raised power 3. And 2 raised power 3 is 8. That's how we got that. Now, the next, let's talk about the operations on sets. Union. The union of two sets combines all unique elements from both sets, denoted as A union B. Definitely, all of you that, okay, majority of you, majority, if not all, you are still going to have a union. You are going to marry. So that is the male and the female. They are totally different sets. The composition of a male is different from the composition of a female. So the male is a set, the female is a set. Then joining the two of them together, it becomes the union. That's how we have the union of a set. So the union is just you combines all the elements. Now, if you see, because we have to like relate it to the real life. In a family, you will say that when a father says this is what is going to happen, the mother will also establish what he has said. That is what we call a union. They both combine. They form that tie that whatever the rules they make, none of the children can break it. So if the mother is, for example, telling the son, don't go out, is late, and the father says, yes, you must not go out, that it becomes that is a union. So they have the same thing, it combines. But it wasn't like that before. But when they married, definitely they have to have a unified characteristics, behavior, and so on, like that. Okay, you're finding it difficult to stay connected. The network is suddenly very bad. Okay. Sorry for that. Now, for example, suppose that we have S as 1, 2, 3, and then T as 1, 3, 5, P as 2, 3, 4, 5. Remember that these sets are finite. 1, 2, 3, finite, contained. T, 1, 3, 5, contained, and then P, 1, 2, 3, 4, 5. Okay. Now, let's find the union. For example, S union T. We are going to combine, so please pay attention. I'm going to combine the element of S and the element of T. But when you are doing that combination, there will be no repetition. Before you call someone your friend, whether a male or female, you call your friend. Now, for you to come together, and there will be some kind of behavior the two of you are having common. If it's not common, definitely what will happen? You will not be friend with the person. So when they call that person, let's say Michael is your friend, Mike is a friend. If Mike is your friend, it means you are having the same kind of behavior. If it is not, definitely you will not make a friend with him. You just go and look for another person entirely. So this kind of the union now. Now, the elements that are the same, you don't repeat them. The elements that are not the same, you write it out. And that is why that when you see friends, they influence each other, not on the behavior that they have in common, but on the behavior they don't have in common. Now, here, 1 and 1 is there already. So I can't repeat, I can't say 1, 1. I can write 1 twice. I have to write it only once. Now, the next is 2. 2 is here, but 2 is not here. No problem. I have to write it down. 3 is here. Yeah, 3 is in the other one too. So I have to write it down. Then, okay, on the T, we have 5. So you just write all the elements. Normally, let me just write let me write it in this format. On a normal basis, it will be like when you say union, you are combining everything together. You are going to write something like, say, I'm combining 1, comma 1, comma 2, comma 3, comma 3, comma 5. This is what you are supposed to have, right? For the union, you are combining all the behaviors together, everything together. However, you don't do repetition. Remember that I mentioned in that LB that you don't repeat elements. So 1 1, you are repeating the element. So you have to pick only one element, 1. 3 3, you are repeating the element. You have to pick 1 3. So I'm going to have 1, comma 2, comma 3, comma 5. So I'm not repeating this one. I'm only writing one of it. I'm not repeating this one. I'm only writing one of it. That's how you know the union of a set. Okay. Then I think, okay, we have not done yet. Let's also look at S union P. So S union P, I'm going to combine S and P. S is 1 2 3. Where's my P? P is 2 3 4 5. So 1 will come, 2, even though there's 2 here, but it's still 2. Then 3, even though there's 3 here, it's still 3. Okay. Then 4 and 5 that is left here. So that's how you have this. Okay. Now, I think that is so simple. If you do not get it, let me know. Now, the next one is T union P. So I think you should be able to do that. T union P will be 1, 2, 3, 4, 5. Yeah, combining everything together. Now, let's look at another one, complements. The complement of a set A encompasses all the elements in the universal set that are not part of A. It is denoted as A raised to power C or A prime. That is A complement. I think I prefer to use C, A raised to power C, for C complement. Okay, for your level now. The A complement, which is this, it means that is the element that is in the universal set but not in A. They are not in A. For example, let U be 1, 2, 3 up to 10, be the universal set, and then let A be 2, 3, 4. A is 2, 3, 4. Now we want to now find what will now be the complement of A. The complement of A is that what are those elements in the universal set but not inside A. Remember that the A has 2, 3, and 4. So that means that 2, 3, and 4, I'm going to remove them completely from the universal set. And I will write the remaining element in the universal set. That is the A complement. So I'm going to have 1, 5, 6, 7, 8, 9, 10. I believe that one is simple to figure out. Next, let's talk about the comparability of two sets. So two sets A and B are said to be comparable if A, okay, is a proper subset of B and B is a proper subset of A. That is, if one of the sets is a subset of the other set. Moreover, two sets A and B are said not to be comparable if A is not a proper set of B and B is not a proper set. So you can't compare them. That's what we call comparability. You compare. But if you cannot compare them, there is not a proper subset of it. For example, we have A to be this and B to be this. Now, I think, let's see, then A is comparable to B because since in A is inside B, okay, it's a proper subset. Since A is a subset of B, okay, A is comparable to that. But is B inside A? So now the next one is disjoint sets. Disjoint set. Now, you know, when anytime you see this is negative, joint supposed to be come together, but it makes it not to come together. You know, sometimes English, just use English. Disjoint sets signify two or more sets that do not share any element. So that is, if A is an intersection of B and is equal to an empty set, that means there is nothing common between A and B. That is meaning of the disjoint. There's nothing common between A and B. They are not friends at all. They don't have anything in common. That's why I said you should be relating it to the real life. They don't have any A and B. So A is a person, then the B is another person. They don't have anything in common. If this one says the other one, we just follow the other way. They just hate each other. So there's nothing common in them. That is disjoint. For example, now we have A to be 157 and B to be 234. Now tell me any element that is in A and also in B. There is no element in A that's also in B. No element at all. So since there's no element in A that is also in B, that becomes a disjoint. And in that case, it becomes an empty set. So A intersection B here is empty. Nothing common between two of them. Let's talk about, oh, okay. Oh, sorry, I think that is another one. Set difference. The difference of two sets A and B denoted by A minus B or A slash B is the set of elements that are in the set A but not in B. Please, all these terminologies, we are going to make use of them when we are going to do some examples. So that's why I'm trying to explain this one further. Now, when you're talking about the difference, difference normally is minus, subtraction, okay? So A minus B. So difference between A and B is A minus B. Difference between B and A, B minus A, okay? They are totally different. So for the A minus B, it means that for the A, please, A minus B, it means that the set of elements that are in the set A, but not in the set B. Yeah, let's look at that. A minus B, A, but X is not a member of B. For example, now we have A to be 1, 2, 3, 4, 5, B to be 3, 4, 5, 6. Now, if you now write A minus B, for example, the elements that are in A but not in B, let's look at it. Let's go to the element. Let's start cancelling out. Element in B, 3. Is it there in? Yes, it's there. Cancel it out. Let's go to the another element. Element 4 in B, also in A, cancel it out. Element 5 in B, also in A, cancel it out. Okay? Element 6, no. Now, we have 1 and 2 left in A, which are not in B. They are not inside B at all. So that is 1, 2 that we have. Now, let's talk about B minus A now. For the B minus A, let me erase this. For the B minus A, what are the elements in the B that are not in A? It's just simple. It's 6. All these 3, 4, 5, they are in B, right? And also in A. But it's only 6 that is in B that is not in A at all. So that is difference, a set difference. Okay. Now, let's move on. We should note that it is important to know that A minus B is not the same as B minus A. Look at this one now, A minus B. Do we get the same answer as B minus A? We do not get the same answer as B minus A. So therefore, you cannot, it is not always the same. Let me also give you just an instance. If you have, let's say A is 5, for example, and B is 2, for example, A minus B should be 5 minus 2, right? That should give you minus 3. Now, B minus A, what of B minus A? That should be 2. Oh, sorry. This first one will give me ordinary 3, not minus 3. Sorry, I'm sorry. Then B minus A is 2 minus 5. That should give me minus 3. Can you see that it's not the same? So there's no way A minus B will be the same as B minus A. All right. Now, let's talk about the symmetry difference of sets. We talk about difference of sets. Now, we are talking about symmetric. Now, the symmetric difference of two sets A and B denoted as A with a triangle B is a set of elements which belongs to either A or B, but not both of them. Not belonging to their intersections. That's the meaning of not both of them. It does not belong to their intersection at all. Okay. Now, mathematically, we can express asymmetric difference B to be A minus B. That means elements inside A that are not in B. You write them out first. Union B minus A. Elements in B that are not in A. You now join the two of them together. That's what we call the symmetric difference. Symmetric means equal. When you say A minus B, you have to do B minus A. Okay? You can't just say A minus B, B minus A. Now, for example, we still use the same element we did the last time. Remember that A minus B was a 1, 2, and B minus A in this case, is 6, not is 6, not 3. Is 6. Now, let's now do A symmetric B, meaning that, there is a mistake here. Please, I'm sorry, a typo error. So it's going to be 1, 2 union 6. Okay, 1, 2 union 6 will give me 1, 2, 6. 1, 2, 6. Because B minus A is that. Now, we can also have B symmetric A, not only A symmetric difference B. You can also have B symmetric difference A. Now, let's do that one. That will be B minus A, union A minus B. Now, there's something you have to pay attention to. The first letter that comes will be the one to appear after that equality sign. For example, now, when we did A symmetric B, A appear first, A minus B, before B minus A. In the second one, B symmetric A, B appear first, B minus A, before A minus B. So you have to pay attention to that. Okay, please, you just pay attention to that. All right, so B minus A and then union A minus B. Here, please, is this 6? Is this 6? That is a typo error that I overlooked. Properties of set operations. So let's talk about the properties of set operation. We have what we call commutative property. Commutative property. Okay, sorry, let me read more. Why? Okay, please. Why others can join and then some cannot join? Okay. Oh. Coming. Sorry, because it's like some cannot still join. I don't know, so I'm trying to like. Okay, sorry for that. Now, for the commutative property, the commutative property has said that the order in which sets are combined does not affect the outcome of their union or intersection. How they combine? Commutative communication. So, sorry. A union B equals B union A. A intersection B equals B intersection A. It doesn't affect whether they combine together, union, or they have intersection. Nothing. So this is just basically that they don't affect each other. They don't influence each other. A union B is the same as B union A. A intersection B is the same as B intersection A. This is commutative. The next is distributive property. The distributive property highlights how set operations can be distributed over each other, akin to algebraic expression. For example, now, when you're talking about distributive, if you are in a class and I try to give you, let's say, test sheet or test script, distribute it. It means you take yours, then you pass the remaining, right? That is the same thing as a distributive property. A intersection B union C. So the A will be passed to B first before it will pass to C. So that is why we have A intersection B. That union doesn't disappear. It will still be there. Then A intersection C. So we are distributing it. It's moving like that. So the A it moves to B, then to C. That is the distributive. All right, next. Associative property. The associative property illustrates that the grouping of sets does not influence the final result of their operations. Now A union B union C. So in this associative, it doesn't affect, it's just the grouping. It does not influence. It's just how you group it. So if I have three students, for example, and they want to write a test, so they sit not too close to each other. If I give it to the middle one first, and I give the script, the test to the next, and to the first, and then to the third one, it doesn't mean anything. It does not affect that final result. It doesn't affect the final result. It doesn't affect. So they will still get that script, right? The test. So A union B union C. It doesn't matter. Remember, but one thing is that is union throughout. Union throughout, meaning that it's the same thing. So if I want to give you a test, for example, for that three, either I give it to the first one or to the third first before the second one, they are all still writing the same exam, and I'm giving them the same time. You understand? So in that case now, it doesn't affect. Now, also, for example, the next one is intersection. Okay, the network is okay. For the intersection, so A intersection B intersection C, it doesn't affect two. The same thing. We have what called identity property. The identity property reveals that the union of a set with the empty set yields the set itself, and intersection of a set with the universal set yields the set itself. Now, I will explain with an example. Now, A union empty is A. Do you understand? A union empty, since A is a set, union with nothing, A is still the A, nothing happens. Or A intersection, I didn't write that, or A intersection empty, okay? And the intersection of the set with the universal set yields the set itself. Now, we have what we call domination property. The domination property establishes that the union with the universal set results in the universal set. I think that's where I mean. While the intersection with the null set results in the null set. Okay. Um, I've moved it from the other one to here. Now, A union universal is universal. A intersection universal is empty. So that's why we have to look at it. Now, the word domination, it dominates. So A union universal, what is in the A and in the universal? Definitely what is in A is already in the universal. And that's why they call it universal, general. That is in all. So A union universal is universal. A intersection universal is empty. All right. Now, the next is a idempotent property. This property shows that the union or intersection of a set with itself yields the set itself. I think A union A is A intersection A is A. Everything in A is still A. Now, De Morgan's law. The Morgan law states that suppose A and B are sets, then A union B complement is A complement C intersection B complement, or A intersection B complement is the same as A complement union B complement. Now, you will see the like a magic there. A union B complement. But when the complement is being distributed to A and B, what happens to it? It's being split. The union becomes intersection. This is what I mean here. When this complement is being distributed to this, which is this one, and when it's being distributed to this one, which is this one, this union becomes an intersection. Likewise, in the other one, when um the complement is distributed to A, which is A intersection, sorry, A complement, and also the complement is distributed on B, which is B complement. You can see that this intersection here changed to union here. So it's totally different. That's for the De Morgan. So we have some identity and name, like identity law, um, domination laws, independent, and so on. Just as laws I just explained. Okay. That would, like what I just explained. Okay. Let's look back. So we have the De Morgan there, the absorption, the complement, the distributive, the associative, the commutative, and so on. Okay. Now let's move on to the next Venn diagram. This is where I want most of you to join so that you understand this Venn diagram. Now, for the Venn diagram serves as a visual tool for representing sets typical composed of overlapping circles, where each circle signifies a distinct set. This visual format facilitates a clear understanding of relationships, unions, intersection, and differences among various sets. Then the Venn diagram is to provide intuitive insight into how sets interact with one another. They enable quick visual assessments of relationships and operations, making the complex set analysis more accessible and comprehensible. Now, A intersection B. This is how you find the intersection is when you have those two rings. The first ring is for A, the second ring is for B. So when you join the two together, just like the Olympic ring, if you see the way of the Olympic. So when you join the two of them together, they intersect, they have common center. That common center is the intersection, and that is why we shaded it. So A intersection B. Then another one is A union B complement. Now, A and B, the first circle and the second circle are this A and B. They come together. Then the complement means nothing can break them. So they come together. The complement is now the outside that A and B. Then we have B minus A complement, which is A union B complement. So the A that is being shaded union the B complement. So anything complement means that you're not going to shade that part. Okay. And the shading has to be with from the universal itself. Then the next one is A intersection B, which in this case now empty set. We're talking about empty because A and B, there's no joining. There's no way you can join the two of them together. Okay. Just take normal ring that you cannot join the two of them together with a physical, except you have to weld it or something like that. So A intersection B empty, meaning that the two set they do not intersect. Then next one is A union B. A union B, since it's a union, is being shaded within the A and B. We didn't shade outside. Okay, everything within A and B is being shaded. So that is A union B. Okay, and when you use union, if the two of them like union, like the marriage, if two of them are hungry, nobody will know that they are hungry. They do not eat or something like that. You understand what I'm saying? Or if two of them are enjoying, nobody might they might just travel and then nobody knows what they are enjoying. Next is B minus A. Okay, B minus A means that what is in B that is not in A. Okay, what is in B that is not in A. So it is a part of the A, some part of the A that are not there. Okay, now after that, this is what you need to know. This formula, the universal set equals n, that is the number of, that is A minus B, that what is in the A that is not in B, plus what is in the B that is not in A, plus the intersection of A and B, and then the union of A and B complement that is not within. This formula is what we need anytime we want to do the calculation. Okay, so we're going to look at that now. So let's look at example. The first example, example 1. A survey carried out on 25 undergraduate students showed that 18 of them ate fried rice, while 20 of them ate jollof rice. Find the number that ate fried rice and those that ate jollof rice if each of them did eat at least one of the two foods. Now, before you start, you need that formula. Okay. Now, remember that the survey is carried out within 25 undergraduates. This is how you find it out. Okay, let's start. Okay. Um, I can do it in two different forms, but let me do it in this way first. Uh-oh. So now we have this. Okay. Now, this is it. And then definitely we are going to have two rings. Why are we having two rings here? Because there are two foods they talk about: fried rice and jollof rice. Okay. Now, they carry this thing out within 25 undergraduate students. That means that is universal. They don't go beyond 25 students. Maybe they don't want to spend more money. That is why they just only figure out 25 students. So that is a universal. They don't go beyond that. So the universal is usually written here, 25. So let's say our U equals 25 here. All right. Now, this we are going to represent, fried rice and jollof rice. So let's say F for fried rice, J for jollof rice. I'm going to use this formula also, but let me first explain a conventional way. So F for fried rice, J for jollof rice, right? Now, let's go back to the question. We are told that show that 18 of them ate fried rice. 18 ate fried, but we are not told fried rice only. There's some students they will eat fried rice and then go again and eat jollof rice. So we are not told that it's only 18 that ate fried rice only. We say 18 ate fried rice, but not only. So those 18, some of them still sneak and went ahead to eat jollof rice. Jollof rice is very sweet. So they have to go ahead and eat jollof rice. Now, if you want to put that 18, you can't put it inside the fried rice. No, you cannot. So what I will do is that I will put that 18 outside the fried rice, because we are not told only fried rice. As soon as it's only fried rice, I will put it inside the box. Now, that is first thing. Let's continue. Why 20 of them ate jollof rice? Also to jollof rice, we are not told that they ate jollof rice only. That word only is where that compliment is coming from. Okay? If you watch the video again, you see where the compliment was only. So it's the 20 of them ate jollof rice, but not jollof rice only. So maybe those, because they have like two groups. Maybe the other group say, oh, after eating jollof rice, they still want to taste fried rice. Now, 20 of them. So I'll put the 20 outside. All right. Now, find the numbers of them that ate and so on like that. Now, but we don't know, since those students one sneaked out after eating fried rice, went to eat jollof rice, and those one that are eating jollof rice still try to like collect fried rice again. So there's a kind of sneaking there. So we don't know how many of them actually ate both fried rice and jollof rice. We don't know. So let's call that letter X. So this center here are those that ate jollof rice and then fried rice at the same time. So let's call it X. Now, I can redraw this. If I redraw this one now, so I have my 25 here outside. I have my two rings. We have fried rice and we have jollof rice. Now, but since I do not know 18 is those that eat fried rice, but not only fried rice. So I have to put that 18 inside. And if I have to put it 18 inside, it means that it will not be what? Oh, okay. Now it will not be 18 minus X. Because I want to know only those that ate fried rice. They did not eat both. Only. So it has to be 18 minus X. So I will put it inside and it becomes 18 minus X. Remember that my center is still X. Okay. Now for the fried rice, for the jollof rice too, if I have to take that 20 inside too, then it will also be 20 minus X. Because I want to know those that only ate jollof rice, not that they are eating the two at the same time, or they ate the two. So they one particular food. So 18 minus X are those that ate only fried rice, they did not eat jollof rice. And 20 minus X are those that ate only jollof rice, they did not eat fried rice. X is the number of those that try to eat fried rice and jollof rice. Okay. 18 minus x. Okay. Oh, you don't understand. Okay, where you don't understand. I hope you didn't join late, right? That is Ayomide. If you don't join late. Now, we have this now. Are you with me? This 18 minus this is this one. Is this first one. That is A minus B. That means those that it's only, remember that when you say A minus B are the elements in A that are not in B, right? So now the A minus B here is now show now since I'm using F and J, so I'm going to change those letters. Now what will I change it to? It becomes U equals N into bracket, sorry, F minus J. I'm not going to use this A minus B again because what we have is F and J, right? Then plus N into bracket J minus F, then plus their intersection. That is a F, that is N into bracket F intersection J, then plus N into bracket A union B complement. Those on the outside. All right. Okay. So now I have this now. Okay. Now, can you tell me where this, you don't understand? Okay, from where? So if I can maybe start all over again. The first thing is that you have to write this formula out. Now, why I'm using A and B is because it's a universal one, like what is usually right. However, the question depends on how the question is. Here we are talking about jollof rice and fried rice. So F for fried rice, J for jollof rice. Please, anytime they do not mention only, make sure that that number you are giving, write it outside. If you are giving those that ate fried rice only, that is time you write that number inside the circle. If only is not mentioned there, don't write it inside the circle, write it outside. That is just the logic. Okay. Then when you have that two rings joined together, that center is those that ate fried rice and jollof rice together. Center. Both. That is what called the intersection. Yeah, because they intersect, they try to eat fried rice, then went ahead and intersect to eat jollof rice. So that is intersection. That is the X we have in. Now, that 18 is the those that ate fried rice. 20 is those that ate jollof rice. Now, you see that I wrote them outside. The mistake where students used to make is that they usually write that 20 inside and then the other 18 inside. No, you don't do that. Except they mention only, the word only. Those that ate, maybe you said 18 of them ate fried rice only. That is time you write it inside. But if that word only is not mentioned, don't write it inside, please. All right. Now, and I try to redraw that my Venn diagram. So redrawing my Venn diagram now that I want to take that 18 inside. If I have to force the 18 inside, that center, which is the intersection, has to be minus. So that means it will be 18 minus x. If I have to take 20 inside, it will have to be 20 minus x. I need to do that in order for me to get my answer properly. Now, here now, I now have some things inside. Now, what of outside, generally outside? Nothing. We're not told that out of that 25, we are not told that there are some categories of people who do not even eat rice, both fried rice, any of them, they do not eat fried rice or jollof rice. We are not told. So that means all those undergraduate students, you understand what I mean? They try to eat something. Now let's assume that maybe 2 or 3 did not eat. Then you bring that number down here, this side that I'm trying to circle here. You write the number here for those that do not eat fried rice and do not eat jollof rice. They do not eat either of it. Okay, but we are not told. So it means that that place will be automatically will be 0. Okay, you might say, oh, they did not. Why are we writing 0 there? We need to write the 0 there to show that, okay, there is a part. This 0 here that I've written is the one that goes here. A union B complement. Now, this one here is this one here. This, sorry. That is not, the A union B, sorry, A intersection B is this. A intersection B is this one. This one is this one. And this one is this one. Can you see how we have figured it out? From there, we can then do our calculation. And oh, and my 25 here, that is here, is this one also. From there, we'll figure it out. If you don't do that, you might quickly not get it. I still like you to start all over again. Hamza, did you join late? You joined late. I'm going to do another example. Don't worry, Hamza. All right. From here now, let's finish up our calculation. Okay. You can see how I've drawn that lines. So it's going to be 25 equals 18 minus x plus x plus 20 minus x. All those numbers I'm going to just be putting plus there, plus 0. I think minus x and x plus x can cancel out. Now I'll be left with 25 equals, well, 18 can add up to 20. I think that should be 38 minus x. You know, this 0 that is outside here, it doesn't really mean anything. Oh, it's like you cannot see there. It's 25 equals 38. Let me write it here. Minus x. So definitely, I think that is 25 minus 38. If you take it inside, equals minus x. Now, 25 minus 38, is that not minus 7? Minus 7 equals minus x. The minus can cancel out minus, x will equals to 7. Okay, so this is I've gotten my answer now. All right, I've gotten my answer. Now, you will now redraw the third one. You know, you now redraw the third one. For you to now redraw the third this thing, diagram. So let me do the redrawing in this one. So if I have to redraw, it becomes 18. Okay. You are lost. Another example is I'm going to do another example. I have 4 examples for 2 by 2 here. So just continue. Pay attention. 18 minus my x is now 7. You know, I've gotten x as 7 there. Then inside, instead of me to write x here, I'm going to write 7 inside. Then the other one will be 20 minus 7. Okay, 18 minus 7 is 11, right? So let me just cancel this and write 11 here. 20 minus 7 is 13. So I write 13 here. Now, let's now go to the question. What the question says? Find the number that ate fried rice and those that ate jollof rice. Both. See this word and means both. So who are those that ate both fried rice and jollof rice? 7 numbers. They are just 7. Okay, you are just coming. Okay. I'll do an example. So 7 of them ate both just jollof rice and fried rice. Now, the second question says, if each of them, where is it? Did eat at least one of the 2 foods. Okay, it's just that it's under the condition. If each of them did at least one of the 2 foods. Okay, so those that ate only fried rice, 11. Those only jollof rice, 13. So we want to know those that ate only at least one food. And you know, one thing about this is that where the 7 came from the calculation we did. That 25 equals 38 minus 7. That is a 25 minus 30. Oh, sorry. I think I made a mistake. It's not, that should be okay, 13. I'm sorry for that. I think that's where I made my mistake there. I didn't subtract very well. Sorry for that. So let me go back. Thank you for telling me that. All right. Thank you for that. Okay. Thank you. Right. I didn't subtract very well there. That is 25 minus 38. That should give me that is 3 minus 13. Sorry. So the answer is minus 13 there. Okay, thank you, Abdul Majid. Is an oversight. Now I got minus 13. Sorry, I got 13 there as my final answer. So that 13 is what I will now put. That will be 18 minus 13, and then 20 minus 13. 18 minus 13 will definitely give me, is that not 5? And 20 minus 13 will definitely give me 7. Okay, so I'm going to have 577 here. Okay. All right. Now 577. If you look at this now, definitely, definitely, there are some people that do not eat, because that will be 5 plus 7 plus 7, and we are saying it's also should be 25, but this is not equal to 25. This is I think 19. So there are some people that do not even eat there at all. Yeah. So let's look at another example. Okay, for those that just joined, I will use this one to in a class of 80 students, every student had to study economics or geography or both. If 65 students studied economics and 50 studied geography, how many studied both subjects? Okay, in this case now, if you still use that formula, but here, remember geography and economics, it has to be G and E, right? Okay, so let's draw that. 2 rings. Use G for geography and E for economics. In a class of 80 students, that means all the universal is 80. So I can put it anywhere, 80. I don't want to put it close to this E. Or should I put it close to the E? Let me put it close to the E. Uh-oh. Okay, so let's do this. So I have my E here. Now I have my 80 as my universal set. U equals 80. All right. Now, every student has to study economics or geography or both. If 65 study economics, they did not say if 65 study economics only. Assuming they mention 65 study economics only, it would have been better. But they did not mention that. So 65 study economics. I will write that 65 outside for the economics. Okay. Now, what is the next one? 50 student, 50 study geography. 50 geography, right? How many study both subjects? We don't know how many that study both all the subjects. So let's say X for the here now. So that means that if I have to redraw I have to redraw it in this form. G for geography here, E for economics. Now, 50 that study geography, but we're not told only. So that if you want to know those that study geography only, the 50 will now come inside and become 50 minus X. 50 minus X. And my X is still inside. Therefore, economics only will become 65 minus X. Okay, 65 minus X. Now, then I can just, okay, the 80 is outside here. Sorry for that. Now, I can then start my calculation. My 80, which is this universal set, 50 minus X is this A minus B. 65 minus X is this B minus A. X is this A intersection B. 0 here, because we are not told that there are some students that do not even offer that do not study geography or no economics. That is no. That way. You know, when you see or, that is a union. When you say no here, so it's a complement. Then they neither study geography nor economics. You lost it there again. Okay. Now we have this. Where do you got lost? Can you tell me, Michael, where you got lost? So now, if we have this, then I can now start. Let me re-explain that side. Okay, but for you that got lost, I hope you understand how I first drew this Venn diagram, then turn into the second Venn diagram, right? Now, if you do so, now let me erase this side, because when you want to do your calculation, you must make sure that everything is inside the circles. The two circles, everything, those numbers will be inside the circles, and it can only be inside the circles except they mention only, and if they not mention only, that means you will be the one to transfer it inside the circle by subtracting it from the intersection. The intersection is the middle one. All right. Now, after I've done this now, based on the formula, that's why I'm giving you this formula, that you need to memorize the formula. But remember that instead of A and B in this formula, it becomes G and E, right? E minus G. That is that is what you have. Okay. Now, this U is the union, which is this 80. This G minus, you can see, this is G. This 50 is G minus the E. Okay. So this is G minus E. This E minus G. This X here is the A intersection. And then this 0 here, because we are not told that none. Maybe another question will mention that. Now, oh, sorry. So let me now, sorry. Now we have this G, my G here. Now, to now do the calculation, it becomes G universal, which is 80 equals, we now start adding it, 50 minus X plus X plus 65 minus X plus that 0. Remember that 0 was not given, but we have to put the 0 there to show that they do not mention students that do not offer neither geography nor economics. So let's continue. That will be 80 equals, I think, minus X and plus X will cancel out. That is how you will know that you are correct in your calculation. Something must cancel out. 50 plus 65 minus X. The 0 does not mean anything. 80 equals 115 minus X. That becomes 80 minus 115 equals minus X. 80 minus 115, if I don't make mistake, that should be 35, minus 35, sorry, equals minus X, where minus will cancel out minus, and then that will imply that my X is now 35. Okay, now, since I've gotten X to be 35, I will then go back to that my Venn diagram, and I will substitute wherever I see X with 35. So wherever I see X, I will put 35 there. Now let's go inside this, that the same Venn diagram here. That becomes 50 minus 35. Then here will be 35. And this one will be 65 minus 35. Okay, that 50 minus 35, I think that should be 15. So let me write 15 and circle it so that we will not make mistake there. Okay, 15. That 65 minus 35, that should be 30. So let me write 30 and let me circle that. And we know our center has 35, right? Now, in this case now, okay, let me just withdraw. Although it's going to be small, sorry for that. So this is my economics. This is my geography. So I have 15 here. I have 35 here. I have 30 here. And I have 0 here. And I have 80. Yeah, 80 here. Okay. So what happened now is that if you had everything inside that rectangle, if you add all the values we have got inside that rectangle, it must give you 80. 15 plus 35 plus 30 plus 0 must give you 80. How can we? Okay, but we can do, how do you write? Right? Okay, I didn't get what you mean by BF. Okay. Now, when you add everything together, you get 80. Now, after you have gotten this one, then we can go to the question and then start getting our answer. Straightforward. The question says, how many study both subjects? Those are study geography and economics. There are 35 that study. Now, let's ask question. How many studied only geography? Very easy. 15. 15 study only geography. How many students study only economics? 30 study economics. How many students study neither geography nor economics? What do you get as answer? 0. You understand? 0 for that one. So that's how you get it. Can I proceed to the next question? Can I? Okay, let me proceed to the next question. We have 4 examples. This is second example. So we're still going to do another example. Pay attention, please. Yeah, you can do the economics before geography if you like. There's no problem in that. No problem at all. You can put economics first before geography. There's no problem there. You can do it any way you want it. All right. Now let's look at another question. In a group of 42 students, each student offers at least one of mathematics and physics. Okay. Thank God for my course now. If 22 students offer physics and 28 offer mathematics, find how many students offer physics only. Now look at that question now. Physics only. In this case now, we want to know the physics only. Now, but before that, remember the general formula? Okay. Remember that in this question now, we are not told that there's a particular student that do not offer physics, neither physics nor mathematics. It shows that physics or mathematics is compulsory that the student must offer one at least, or you can offer two, but you should not be like you don't offer any. Most I think you are a science student, right? So math, physics compulsory. Without both, either okay, without both, you can, if you are in I think biochemistry, I don't know if physics is compulsory, but math is compulsory. So you have to have either of it, the two. Now let's now do our calculation. First, let's draw. You just have to quickly do it and then figure out the answer. Now, in a group of 42 students, so that means my universal set is 42. There are no more than 42. All the students in the group, they are no more than 42. That is 42. I hope you can see my 42 very well. All right. Each student offer at least one of mathematics and physics. So let's draw math, physics. So M for math, P for physics. If 22 students offer physics, 22 students offer physics, but they did not say physics only. So you put it outside. The next question is 28 offer mathematics. So 28 outside. They did not say 28 offer mathematics only. All right. Find how many students offer. Let's do our calculation before we know how many students offer this. Now, in between, they did not even tell us those that offer mathematics and physics. Since they did not tell us, so we have to use letter X for that. Oh, you might be saying, why am I using XX every time? In mathematics, we usually like to use X. So, well, you can use any other letter you like. P, K, M, Z, and so on. All right. And also, they did not tell us that there's a particular student or students that do not offer physics, neither physics nor mathematics. None. So that means there's no student that do not, all students must do something. So we'll put 0 there. At that corner, that's why I'm always after that corner. That corner is those that do not do any of that course. Okay. Now, I have to redraw my diagram again. What will be the question before? Can place it inside. Okay. If you want, what the question will say, okay, that's 0 that I put. The question will be after before that question, find how many students in this question before this you see family. They will not say 13 students offer neither mathematics nor physics. That word neither nor is usually that down part. That's where we place it. I hope you understand now. Well, Etu Dayo, Michael, okay. I hope you understand this now. Now, let's now redraw. When we redraw this one, the first circle and the second one, my M for mathematics, my P for physics. So now, that 28 now, that it has to go inside. It becomes 28 minus X. The center becomes X. Okay. Thank you for getting it, Hamza. Then, for the P, it becomes 22 minus X. All right. Our universal set here, Adamo, you tell me where you don't understand there. My universal set here is still 42. Tell me the particular place you don't understand, or the particular part that you don't understand. And then the 0 is here. Now, let's do our calculation. Should we do it down? Okay, let's do our calculation down. That becomes, our universal set is 42. Now, you see that we have put everything inside. Immediately you put it inside, then you can then start your calculation. 42 equals 28 minus X plus X. Everything that's inside, that's the two circles. You add all of them together. 28 minus X plus 22 minus X plus 0. Okay, you don't understand the filling in the diagram. Okay, in the Venn diagram. Okay. When they do not mention only, that word only, if it is not mentioned, whatever the number you're writing, write it outside the circle. And when you want to bring it inside the circle, make sure you subtract it. You subtract the center from it. The center is the X, right? The center is the X for everything. Well, center of the two rings is the X. So you must subtract it from any of them that you are bringing inside. I believe you understand what I'm saying now. All right. Now, this will now be 42 equals minus 8. Minus X has cancelled out X. So it becomes 28 plus 22 minus X. Then that plus 0 doesn't mean anything. So let's just throw that one away. That's become 42 equals, when you add this one together, that is 0, 50, right? 50 minus X. So that becomes 42 minus 50 equals minus X. So let me still do my calculation here. 42 minus 50 will give me minus 8 equals minus X, where minus cancel out minus, X equals 8. Okay, so I've gotten my X as 8. Now let me redraw another Venn diagram here. And anywhere I see X, please, we'll replace it with what value? 8. We'll replace it with 8. Now, the first circle and the second circle, the M. Now, instead of you to write 28 minus X, it becomes 28 minus, okay, let me write it there, 28 minus 8, because 8 is, my X is now 8. 28 minus 8 is 20. So let me write that 20 big. The center now is X, but it's not X we're going to write. We are going to write the value 8. The other one is 22 minus x minus 8 now. 22 minus 8. Okay, I think that should be 14, right? 14. So you can see now, and our 0 is here. We can see now that we have already done everything inside the circle. If you don't do it inside the circle, it's very, very difficult to do. Now, what does, oh, okay, I didn't put physics in that one. Sorry, I just wrote only M, there's no P. P for physics. I thought they supposed to be equals to 0 because 0 is outside. No, no, no. The 0 that is outside is still inside the box. Do you understand what I'm saying? That 0 that is outside the circles, but it's still inside the rectangle. Therefore, it must still be inside plus 0. Okay, I hope you understand Sulaiman, right? Okay, I should come again. That 0, because Sulaiman has that, I thought the is supposed to be equals to 0 because the 0 is outside. Please, how is it now? That 0 that we have plus 0 there, that 0 is not, remember that that 0 is not within the circles, and that 0 represent that those that do not offer physics, and they do not offer, neither do they offer mathematics. That is the 0 we have, although it's not given in the question. And someone asked me, how do we know what to place there if it is other number? It can be other number. Immediately they mention that, okay, um 8, or let's say 7 people, 7 students do not offer physics, nor, that is, they do not offer neither physics nor mathematics. Immediately you hear that neither nor, it is that outside you put it. And when you put it outside, you are not putting it outside the box. So you are not putting it outside the rectangle. You are only putting it outside the circles, but down part of it. And you can see that universal. I wrote the universal on the rectangle. On the rectangle. I didn't write it above the rectangle. I didn't write it below the rectangle. I wrote it on the rectangle to show that that is the universal that encloses everything. That 0 is inside this rectangle, but not inside the circles. So they are not inside this. The 0 is not inside the circle because they do not mention that nobody, there's nobody offering maths nor physics. Nothing like that. I hope you understand this now. All right. Now, from this thing we have gotten now, M, 28 and 14. That 20 represent those students that offer mathematics only. That's the meaning of that 20. That 14 represent those students that offer physics only. That 8 represent those students that offer mathematics and physics. There's no only in that one. That offer mathematics and physics. Then that 0 down in the last diagram, the third diagram, that 0 down means 0 is the number, that is the number of students that do not, that neither offer mathematics nor physics. That is the 0 there. So now you see that we can easily find out our answer here. Find how many students offer physics only. 14. That is just it. 14 offer physics only. Now the last question before we call it a day. Then if there's any, you can still shut me up. Okay. A panel of 10 interviewers was to interview 2 candidates, A and B. Okay, now this one's not A and B. To decide who was suitable for a job. 7 said A was suitable, 5 said B was suitable, while 2 said neither. Now, look at that. Look at that. That question we are talking about where we are using 0, 0. So you can see that they said 5, Y2 said neither A nor B. You can see that word neither A or B. We're going to use it. Now the question is how many students said both A and B were suitable? How many said A alone was suitable? We are now, let's start our, forget about the question. Let's draw our Venn diagram. Let's do our calculation, and then the next we'll know what to do. Okay. Draw the rectangle first. Oh, okay. Sorry. The formula is still going to be there, so I have to erase this. Okay, now I have this first rectangle, circle, and the second one. Now, let's say this is A and this is B, based on what we are giving, A and B. The universal is 10 interviewers, 10. Okay, my U is 10 here. Okay, can we do a Venn diagram example that has neither? That is what we are doing now. Sumaila. So that's what we're doing now. 10. That is the question we're doing now. Okay. Now, what was the question? Two candidates, A and B, decided who was suitable. 7 said A was suitable. So 7 said A was suitable. But did not say only. Not that 7 said A only was suitable. They just say 7 said A was suitable. So 7. 5 said B was suitable. 5 outside. Y2 said, can you read the question now? Y2 said neither A nor B was suitable for that interview. So I'm going to put that 2 down here. Can you see it? Sumaila and others that are asking question. Can you see that 2 that I wrote down here now? So those are the ones that are neither nor. Okay. Now the center, we don't even know how many we are interviewing for A and B. So let's call it X. Okay. Now the next is, let's redraw the diagram. Big one. Another circle. Our universal set is 10. Now our 2 is outside here. Please don't forget that 2. That is still. Now my X is at the center, right? Now if I want to take the 7 inside, it becomes 7 minus X. If I have to take the 5 inside, it has to be 5 minus X. Okay. So that is, then this is A, and then this is B. All right, so let's do our calculation. Now it becomes 10. Remember that 7 minus X is the same thing as this A minus B. I've explained that one earlier. Let me erase this. All right, now let's do our calculation. Our calculation is 10, which is universal set, equals everything inside that universal. The rectangle, sorry, the circles and those one that is not inside the circle, but everything inside. That is why I have to write the universal set first. 10 equals 7 minus X plus X plus 5 minus X plus 2. If you're having bad network, you can rewatch the video anytime you like, or you just, you rewatch. Now that becomes 10. I think minus 7 and, sorry, minus X and X will cancel out. So I'm going to have 7 plus 5 minus 2 minus X plus 2. That's going to give me 10 equals 7 plus 5 is 12 plus another 2. That should be 14 minus X. Don't forget about that plus 2 that is there. 14 minus X. No, I transfer that to the other side. It becomes 10 minus 14 equals minus X. Now, 10 minus 14 is minus 4 equals minus X. This minus cancel out this minus. X equals 4. Now, let me redraw that this side here. Sorry, I'm very sorry. So let me redraw. Okay, so I have this. Remember that up here is 10. That's our universal. Now, then I have my 2 circles. Okay, one is a The other one is B. And I have here outside 2. Remember, is that 2? I have it here. Now, based on this 7, you know, here is supposed to be 7 minus x, right? And my x now is 4. 7 minus 4. 7 minus 4 is 3. So I'm going to have 3 here. My center here is the x, and I've gotten 4 already. This one is now 5 minus x. My x is 4 that I got. So the answer is 1. So that means I can just go ahead and erase this thing. And erase 7 minus 4, which is 3. 5 minus 4, which is 1. So now I have this now. So from here, okay, from here, let's now start answering our question 1 and 2. How many said both A and B were suitable? Both, meaning where they intersect. Both is in where they intersect, or is the union. Now, how many said both? That is 4. So our answer here, how many said both are, the answer is 4. The second question, how many said A alone was suitable? Do you understand what I call A alone? A alone is A only. Okay, 4. Yeah, thank you. Read 1. Thank you. Okay, A alone was suitable. A alone means A only. Okay, that's the meaning of A alone. A only. So A only, only A, only A, only A. Where is only A there? 3. 3 is the answer for that one. 3. How many said A only was suitable? 3. That's how you get that. So I think is somehow easy to understand this Venn diagram. I'm supposed to move to quadratic, but I will do quadratic later. I think I think you all understood how we got that 4. Now, okay, so this will be the end of today's lecture. We will communicate again and have our lecture next time. If there's any question, please just you can drop it later as comment, then I will get back to you. Thank you so much. So thank you all. How do we get plus 4? Why do we get plus 4 and then plus x? The x is the center. The x is the center there, okay? That is those that A and B. A and B. So we see later. Thank you all.